Hello everyone, this is our sensors and transducer lab, and in this lab today we are going to perform an experiment which is related to measurement of speed, right? So we are going to measure the measurement of speed, that means any rotating shaft which is rotating, we need to measure the speed of that rotating shaft in terms of RPM or RPS using an inductive proximity switch. So the principle is based upon the working of inductive proximity switch. So let's see how inductive proximity switch works. Here in this experiment our aim is to determine the speed using inductive proximity switch, and the apparatus required is this setup, which is called as inductive proximity switch for speed measurement, which is developed by Inventec. Here you can see there is a digital counter. As you well know, the purpose of digital counter is to count the pulse rate, right? And here it is a timer. Timer will count the time in seconds, and this is the input supply for the proximity switch. Input supply from the proximity switch to the rotating object, which is our DC motor. This is the DC motor. So here you can see this is the sensor and motor is this one. So along with this motor a disc is connected. In this disc a metallic object is associated with it, right? So whenever it will rotate, it will sense by this proximity sensor, and the output we will get in terms of pulse count, and then we will calculate the speed from this. So this is the motor connection. Motor connection is connected to here. Two terminals are here, positive and negative. This is the motor connection, and there is a knob by rotating which we can easily increase or decrease the speed of that motor. And this speed is unknown. We have to determine this speed from these two observations, right? So we will see how it works. So you can see this is the basic block diagram of this inductive proximity switch, where target metal is here, it is shown, and high frequency magnetic field direction is this side. This is the internal circuit, and sensor is placed here, and sensing coil, here is sensing coil, and high frequency magnetic field is there. So whenever the target metal passes through this sensor's field, an eddy current will build up, and it will reduce the sensor's own oscillation frequency, right? So here you can see each and every time this shaft rotates and this metallic object passes through this sensor's field, every time it passes through this, an eddy current will build up, right? And in this digital counter the pulse count will be counted, and this is the timer. So let's see how it works. We need to power on this. This is the reset button. After taking every readings, we need to reset so that the pulse count should be again back to 0 and timer should be again back to 0. So we have taken a standard time, suppose for 5 seconds. After every 5 seconds we are going to take the readings, right? So here in the observation table you can see this is serial number, how much number of readings we are taking, pulse or digital center, that means pulse count, whatever count it is, we need to write down here, and the timer means time in seconds, and after that speed, pulse per time, that means this divided by this is equal to this is in revolution per second or per minute, which is the speed of the rotating shaft, right? So let's start with this procedure. There is uh, there is a button and a toggle switch, you can see. Start and stop. Start means it will start counting and the timer will start whenever we push that switch. And here is the another switch which is used for starting and switching off the motor, right? Whenever we push that switch this in this direction, the motor will get start, right? So let's start. We have started the motor. So I am switching on the motor here. The shaft has started rotating. Initially it's taking some time. Here you can see it's started rotating, and I have kept at a minimum speed. Here I am starting the digital counter and the timer. Press the reset button. I have taken time of 5 seconds. After every 5 seconds I will take the reading. So here the count is 10, right? At 5 seconds it is 10 counts and the time is 5 seconds, right? So it will be 10 by 5, that means 2, right? So initially actually in the first reading it came 4.9 because it is operating manually, so exact at 5 seconds it is very difficult to stop. So around that 5 seconds whatever reading we are getting, we are taking that reading for. So here 10 divided by 4.9, right? So it will come around 2 point something. So we'll calculate this afterwards. Let's take few of other readings. So I am increasing the speed a little. It is increased. So now we will start and press the reset button. It is 26 at 5 seconds. The second observation is 26 at 5 seconds. So this will be 26 divided by 5, right? Now I am going to increase this further a little bit and start again. Press reset. .8, it is 39. It is 39 at 4.8 seconds. So it will be 39 divided by 4.8. So this is I am taking as 5 second for standard for each and every observation, but we are operating manually by hand. So exactly at 4.9 at 5 it is very difficult to stop each for each and every observation at exactly at 5. So it is having some little difference, but that doesn't mean that at every 5 seconds I have to take. You can take at different timings because it is not any standardized time. So I have taken 5 seconds, so for all the observation I have to take the similar. If I would have taken 10 seconds, then after every 10 seconds the pulse count I would have calculated. I would have observed and then calculated the speed of the rotating shaft, right? So let's see for the next observation. Increased a little more, start again, reset, reset, 5.1, it is 60. It is 60 at 5.1, so it will be 60 divided by 5.1 here. $66. So now I'm going to take 8 readings. Again start, reset, 77. For next reading it came 77 pulse count for 5.1 seconds, right? So you can see the speed is gradually increasing, right? Speed is gradually increasing as I have increased the speed of motor by using this knob. $86. Here for the next reading it came 86 for 5.2 seconds. So you can calculate from these two readings, as I have shown. The initial reading as 10 by 4.9, it is 2.04. So the rest of the reading similarly you can calculate from these two. So the next one more reading I will take. So these 8 observations I will keep. For it came a little more, so I am taking this observation once again. 90 or 4.8. So these are the observations for determining the speed of a rotating object by using inductive proximity switch, right? So 8 observation I have taken from here, and from these two readings I can calculate the speed of the motor, which I have initially shown here. This is the sensor and this is the DC motor. This is associated with this one. So the speed of the motor can be calculated from here using this inductive proximity switch principle. So just turn off the motor and switch off the circuit, and just the rest of the part is calculation of speed from these two. This is the whole experiment of determining the speed of a DC motor. Here DC motor has been used, any rotating object can be used. So of a DC motor by using inductive proximity switch or inductive proximity principle, which is based upon electromagnetic induction, right? So that's all.